This video is about alternative power sources. It is the third video on Topic 8, Energy Production, of IB Physics. This is part of the core material, so it's the same for SL and HL students. Take a moment and read the success criteria that we will cover in this video. Pause it if you need to. So in the photo we have a solar heating panel. These panels have a black background in order to absorb more of the radiation from the sun. Notice the liquid flowing through the panels is not the water that goes to your tap. It's a heat exchanger, like we discussed in the nuclear power plant and the other ones in the previous videos. This particular design also has an electrical heater in case there's not enough heat from the sun. In contrast, the photo here shows photovoltaic cells, sometimes referred to as solar panels. It is important that we distinguish these two types of panels, however, as this one creates electricity and is not based on just thermal energy. Some textbooks go into detail about how the potential difference is created between the different layers. I believe it's enough for students to realize that the sunlight causes changes in the layers to allow electrons to flow in one direction, creating the potential difference. If you're interested in this, please check out your textbook for more details. And again, just like all of the other types of energy production, make sure you know some advantages and disadvantages of each source. Let's look at some of the energy transformations behind creating energy from wind. Some people might be surprised by us putting solar energy first, but it really is the beginning. The sun is going to heat different parts of the earth in different rates. This temperature difference will cause hot air to rise and cold air to fall in different places. The resulting in different pressures will cause a general movement of air, which we call wind. That wind will have kinetic energy of those air particles, of which we need something to turn the turbine and create electrical energy. So let's derive a mathematical formula for the power delivered by a wind generator from the kinetic energy of the wind to the turbines. The area that would be encompassed or swept out by the blades, in this case, would just be a circle. We could calculate the volume of air moving per second through this by the speed of the wind times the area of the circle. Now I want to incorporate the density of the air. So you can see at the top in blue, I've rearranged the equation. So the volume of air we're talking about going through would be the mass of the air divided by its density. So I've substituted that in here. If I rearrange this, I can have mass then per time, or mass per second, will be the speed of the wind times the density of air times the area that the blades of the turbine will encompass. Now you might wonder why I went through all of this. Well, it is important because I want to be able to calculate kinetic energy, which has a mass inside, and it's not very easy to get the mass of air. Okay, so the mass of the air per second will be given by the speed of the wind times the area times the density. So if I put that into my kinetic energy equation, and I do the kinetic energy per second, because I have the mass per second, I will get, okay, let's substitute that in. Let's clean that up a little bit. Now, why did I want kinetic energy per second? Well, energy per second is just the power. So we can say the power is given by this equation here. And yes, that's the one you find in your data booklet. So anyone in my class knows I love that data booklet. But it's also really important you know that this equation refers to wind turbines and what each of the different variables are used for. The other really important thing about all the equations in that data booklet is realizing some of them have limitations or assumptions that are made when they are derived. For this one, in this case, one assumption was that all of the kinetic energy of the wind was actually going into causing the turbines to turn. Now, if the wind actually is moving through, then it wouldn't have been able to give up all of its kinetic energy. If not, it doesn't continue to flow. It also means that we don't have any friction going on, transferring some into heat. But please be really careful when questions are asked about what part of the turbine or what part of the power transformation is being talked about. And here are some advantages and disadvantages. Like all the other times, make sure you know a few of them. Okay, let's move on. Hydroelectric plants. So this is the idea of using water, typically fast from a river or waterfall, or created an artificial dam. Somehow we're going to use the gravitational potential energy of that water, causing it to flow, eventually turning it into electrical energy. Note, I could have started this transformation again because the whole reason why we have water in those different situations was due to the water cycle, which again is caused by solar energy. In addition to the types of hydro plants you might find at Niagara Falls or those created in Norway, there's also the idea of a pump storage hydro plant. The idea is it's better to keep your power plants working at a continual optimal rate, but as people, we use less power at night. So what do you do with that excess power? The idea is you pump it back up to the top reservoir so that you store it again to be released when you need to. So there's a lot of different pieces to understand here, and I've shown a link to a really good video describing what and why you would do this. I'll put the link in the description below. Another way to use water to create energy is by using tides coming in and out of the bay. I'm not sure what happened to my bullet points here, but push pause and please read through how we could use the tides coming in and out to create some electricity. So let's try a question. On the left is a picture from the side, whereas the picture on the right is supposed to be like a bird's eye view. Let's estimate the average power with a range of 7 meters and a basin of 520 kilometers squared, given that the tidal period is around 12.5 hours. First, let's think about the gravitational potential energy of the water that's behind the dam. It will be 1/2 mgh, as 1/2 h will be the average height of the water. And energy divided by time is power, so the power we will get will be mgh over 2t. In order for our answer to be in watts, that time does need to be in seconds, not hours. In addition, in green, you see I'm using that density formula again because we don't have the mass of the water. But using density, we'll know that the mass will equal the density times area times the height of the water, because I have the area given to me, and we also know that the change from the bottom to the top has given us 7 meters. Let's put all this in and see what we get. Push pause and calculate yourself first to see if you get the same answer. So, did you get 2.8 gigawatts? Couple things I want to point out. Yes, this question needed to know the density of water. You don't have to have that memorized, although I would suggest that knowing 1 gram per centimeter cubed for the density of water is a good idea. Secondly, it would have to be given to you. One of the things that is given to you is the value of G, 9.81. I want to just remind everyone that you really should use the values of any constants given in the data booklet as given, and not just their average values, or maybe a value you've memorized before. One more time, some advantages and disadvantages of hydroelectric plants. One last brief idea: oscillating water columns to generate electricity. I've seen this question, it was in previous syllabus, and I've seen the question in relation to simple harmonic motion as well as the waves coming in. Here's the gist. As the waves come in, you can see that the water levels right here will rise and fall. That will increase the pressure in that air column, and the changes in pressure will cause air to flow through this Wells turbine. Basically what that is whether the pressure is increasing or decreasing, it will always turn in the same direction. If I have a generator that's being forced to turn, I can create electricity. Okay, so that's the end of the video. Here are the success criteria. Please read through them again, and I hope that you can meet all these criteria now that you've watched.